All right, welcome everyone. This is the video tutorial for the Spectral Lines Lab for Honors Chemistry. All right, so quick little review is that light are particles that travel as waves. So you'll see that there is this wave-like behavior and an origin. The length of the wave from crest to crest is called the wavelength. The height is the amplitude. Okay, the frequency is how often you see a wave go by a place in a given second. So it has the units of per second or hertz, and we use the Greek letter nu, which looks like this funny little V here, in order to represent that. Okay, the longer the wavelength, okay, the lower the frequency, the shorter the wavelengths, the higher the frequency for our waves. When it comes to this electromagnetic spectrum, we see that all light travels the same speed in our vacuum, okay, which is 3.0 times 10 to the eighth meters per second. So there is this inverse relationship between our wavelength and our frequency because when they're multiplied together, we get our constant 3.0 times 10 to the eighth. Now, Max Planck found that there was a direct relationship between the frequency and the energy of a photon. So, if we had a wave with a long wavelength, and so the lambda is high and our frequency is low, the energy would also be low. But if we had something that looked more like this, we see that the wavelength is pretty big. I'm sorry, the wavelength is indeed very small. The frequency is pretty big, and the energy of that wave would also be big. So there's a direct relationship between energy and frequency. Now, what we're going to do in the lab today is look at the spectra. The spectra, or spectrum, singular, is when light is shined through a prism, a diffraction grating. And that is going to make a different separation of the color, just like of rain does to white light as a rainbow. Okay, a continuous line spectrum is what we see through white light, and an emission line spectrum is what we see whenever we have anything else. Okay, so that's what we are going to look at in this lab. Okay, different elements emit different types of spectra because they have different amounts of electrons in different positions that are excited and release different amounts of energies. So here we see at 400, 500, 600, and 700 nanometers in length, we see the purple, then green, then blue, then green, then yellow, then orange, then red um, wavelengths. Okay, so in class I will show you this video. You can play that through YouTube as well, showing how this experiment is actually run. And what we do is we look at this spectroscope, which has a little diffraction gradient up at the top and a little measurement down at the bottom to show you how far each one of those lines are going to be. The 7 down at the bottom represents 700 nanometers, 600, 500, and 400 nanometers. Okay, so here we have two different examples. This is a neon lamp and a hydrogen lamp. Notice that neon has 10 um, electrons and has a different color emitted than hydrogen with just one electron. Okay, in this hydrogen emission spectrum, if we look at it through a diffraction gradient, and I show you a video of that there, you see that there is a red line, there is a teal line, and there's this purple line. Well, if we look at it through the spectroscope where they're measured, you see the red line, the teal line, and the purple line is actually going to be a blue line and a purple line that's spread out a little bit more. Okay, in the lab, what we're going to do is we are going to calculate the wavelength, the frequency, and energy of that red line. So you're going to have to estimate how far this distance is right here, and then you're going to calculate the wavelength and turn it into meters. Then you can calculate the frequency and then the energy. Okay, for neon, you can do something the same, and here I show you the video of that. And then here you can see the diffraction gradient um, of the neon emissions. And this specific shade of dark orange is going to be a mixture of all of these electrons, this one, and this one, in order to make that exact shade. So in the lab, we do the same thing. We're going to try to determine the wavelength for the shortest green line in neon. So if we look for the shortest green line, we're going to look at closer to this end with 400 nanometers. So that's going to be a line right about here. And we'll calculate the wavelength, the frequency, and the energy of that. We do the same for helium, but for the violet line, as you can see here, and for Mercury, which is the longest green line. So we're going to go over to this Mercury line right here, which is going to be in between the 550 and the 600 nanometers. Lastly, you can identify unknowns using the same work. So this is what I'm going to show you in the lab. You're going to click on this website here from the good people at Penn State, and you will be able to click on the period 2, which is the row 2 for the periodic table, and go through and determine which element from the second period each of those spectra is for. Okay, so what we're going to do is then go over to the Spectral Lines Lab, which you'll see in Google Classroom, and you can read through the exact same stuff that I just went over with frequency and wavelength and our equations here. And you can see that there are different kinds of wavelengths and spectra for our different elements. And then here is your screencast video, another embedding in there. You have these pre-lab questions to answer before you turn in anything else. It says, what is the conversion factor between nanometers and meters? You might remember nano. 1 nanometer is equal to 1 times 10 to the negative 9th meters that we got from our chapter 2, where we were doing our metric prefixes. So if we're converting 700 nanometers to meters, we use our dimensional analysis to do exactly that. 1 nanometer is 1 times 10 to the negative 9th meters, and that is going to be 7.0 times 10 to the negative 7th meters. Okay, when we ask for the speed of light equation, I'm asking for this equation, and their relationship between frequency and wavelength is going to be inverse, because when one goes up, the other goes down. And the Planck's law equation is E equals h nu, and the value for the Planck's constant is 6.63 times 10 to the negative 34th joule seconds. So make sure that you answer those fully before we begin the lab. As we go through, you are calculating your different spectra. Okay, so what we're going to do here for hydrogen is show you how to do exactly those. All right, so the red line that we see, I suspect is right about here, a little bit greater than 700. There are 4 lines between 700 and 750, so this is not 710. I would consider this to be approximately 702 nanometers. So I want to convert that into meters. So 702 nanometers into meters. 1 nanometer is 1 times 10 to the negative 9th meters. What that does is it cancels out my nanometers and nanometers, and I get 7.02 times 10 to the negative 7th meters as my wavelength. So now when I do a calculation, what I'm going to do is I am going to use the C equals lambda nu equation to figure out the frequency. So I can rearrange this to get C over lambda. C is a constant, 3.0 times 10 to the 8th meters per second. And I'm going to plug in the wavelength that I just converted. So I'm going to plug in 702 times 10 to the negative 7th meters. And when that happens, I see that meters and meters will cancel out. I put it into my calculator very carefully using the correct buttons, which is going to be 3E8 divided by 7.02 E negative 7. And I get 4.27 times 10 to the 14th reciprocal seconds. This is the value that I'm going to plug in here. Okay, so lastly, what I am asked to do is calculate the energy. E equals h nu, where h is equal to 6.63 times 10 to the negative 34th joule seconds. And then I plug in my value for the frequency that I calculated. And what that allows for me to do is cancel out seconds and per seconds. And in my calculator, I would put 6.63 E negative 34 times 4.27 times 10 to the 14th. Whoops, which is going to be E14. I forgot what I was doing there for a second. So this in my calculator is 2.83 times 10 to the negative 19th joules of energy. All right, so these are our three values that we calculate for hydrogen, specifically for the red line, which we mark right there. Notice how each answer is used in the next calculation. So you'll notice that for the visible light spectrum, that you will always see a wavelength that's going to be 10 to the negative 7th, always see a frequency, which is 10 to the 14th, and always have an energy for that photon that is 10 to the negative 19th. So it's a nice little way to check yourself there. Lastly, you are going to calculate your neon, your helium, and your mercury in the same way. And then you can use this fabulous website from the good people at one of the satellite campuses at Penn State in order to look for the period 2. You're going to click on lithium. Oops, not that. You're going to click on lithium. You see this come up, and you can compare that. I'm using my Duale screen to split. And you can see if your lab is going to match what you see. All right, does this match any of the things that we see? You might have to change the zoom a little bit if you're going to split the screen, but I do highly suggest that you split the screen so that you can go back and forth and show exactly where you're looking at. Okay, hit the back button to check beryllium, see if beryllium matches up with one of them. The back button to look up boron, all right, etc., as you go across this period 2. Okay, and then lastly, you will see that you are expected to answer who has the higher energy, the red or the violet end of the spectrum, and what do we know about energy and frequency. And then you are expected to write your first conclusion. Okay, I have lots of format options for you to look at, but I'll go over this in class with you as well. A sample conclusion as well as a sample lab report conclusion, which I outlined for you, where you are answering specifically what the purpose of the lab is going to be. Okay. You're going to restate your data for hydrogen, neon, helium, mercury, and the unknowns. Give me a how or a why. Okay. Identify the variables. So what did you change? What was dependent on that? And what was the same for each one of these up in the top part here? And then we're going to talk about our possible sources of energy, or not sources of energy, sources of error, and a suggestion or an alteration for the lab. And then in conclusion, wrap everything up with a nice concluding sentence, which